Okay, now we want to talk about the concept of equilibrium. So what does it mean when two systems are in thermal equilibrium with each other? So we're going to say that we've got these two objects, and one of the objects is at 100 degrees Celsius, and then the other one is going to be at 0 degrees Celsius. Now, it doesn't make any difference which unit that we use. So this could be 100 degrees Fahrenheit or it could be 100 Kelvin. So, but I'm just using degrees Celsius. So this one's at 0 degrees Celsius, and then we're going to put them in contact with each other. So when they come in contact with each other, heat is going to start to flow from one of the substances into the other substance. So the definition of heat, Q, was it's the movement of energy due to temperature differences, and it's going to cause the molecules to change their average kinetic energy. So notice that this one over here is hotter than this one. So let's illustrate it by saying that inside of this box, let's say it's a gas. And so these molecules on average are moving much faster than the objects that are in this box over here. So in this box it also has some gas, but it is moving slower. We're going to put them in contact with each other, and so in the same way that the thermometer, when one molecule would hit the side of the thermometer, it would transfer energy into the thermometer. So when we put these two objects in contact with each other, the molecular motions over here is going to start to cause molecular motions over here. And so as energy is being transferred from this object to this object, these objects are going to start to slow down. So these, on average, these molecules are going to start to lose kinetic energy. The energy is being transferred over to here. And so these are going to start to go slower. So let's make these arrows now slower on average. Now they still can, sometimes they can have a great deal of energy, but remember that on average, when you add them all together and average it out, they're going to be moving slower now than what they were before. Now that energy is going over here, which means that these are going to be speeding up. So one's slowing down, the other one's speeding up. Now remember that temperature is a measurement of this. So temperature is going to be a measurement of the random motion of these molecules, so that as these have less energy, they're also going to have less temperature. So the temperature of this one is going to start to go down, and then the temperature of this one over here is going to start to go up. So the question is, well, when do they come to equilibrium? Well, that's going to be when they have the same temperature. So now notice that when it comes to equilibrium, this one has 50 and this one over here has 50. Now don't get the idea that the temperature or the movement of energy is one way. So on average, the energy is flowing from this one into this one until it comes to equilibrium. But also remember that because this has some energy, it's going to transfer energy in this direction back into over to here. But because this is at a higher temperature, the energy is moving at a higher rate in that direction than it is in this direction. So the net flow of energy is going to be in this direction until they're both at 50-50. Now, when they're at 50-50, don't get the idea that it stops, because this is still going to be sending energy over into this container, but it's going to be sending it over at an equal rate as the energy is going back over into this container. So when it's at 50, then everything is at equilibrium, and so the rate of the energy transfer in both directions is going to be essentially the same. So here are some typical temperatures in Kelvin. Notice that you do not say the degrees Kelvin, you just say the word Kelvin. All right, let's take a break, and when we come back, we're going to start talking about the ideal gas law.